Transformer calculation based on load characteristics. Hello everyone, my name is Rafael, I am an electrical engineer, and in this video I'd like to speak with you about transformer calculation based on load characteristics, and to do so I chose this simple exercise. I'm going to read the problem. Consider a distribution network built to supply 3 consumer units. Measurements were carried out to evaluate the characteristics of the loads of each consumer unit for the installation of a transformer as shown in the table. These are the characteristics of the loads. Neglecting feeder power losses, check the alternative that presents the lowest rated power of distribution transformer capable of simultaneously supplying the 3 consumer units connected to it. Okay? This is a simple question, and the key to answering it is to sum the complex powers of the loads. Okay? And the transformer is going to be the complex power of the transformer is going to be equal to the sum of the complex powers of load number 1, load number 2, and load number 3. Okay? We are going to use these values here to calculate the apparent power of the transformer. Okay, for load 1, we see that P is equal to 10 kilowatts. The problem gave us this. And we see also that Q, the reactive power, is equal to negative 2.5 kVAR. Then the complex power of load 1 is going to be equal to S1 equal to 10 minus J 2.5 kVA. Okay? This is the first result. Now we are going to move on to load number 2. I'm going to erase it here. Okay? And write for load number 2. As written in the table, for load number 2, we have that Q is equal to 30 kVAR, and the power factor, lagging power factor, PF, is equal to 0.8 lagging. Okay, what we want is S2, okay, the complex power, and S2 here, phase 2, phi 2. This is the apparent power, and this is the complex power. The apparent power is the magnitude of the complex power. How do we calculate the apparent power? Let's do it. First of all, we are going to calculate the angle phi 2. Phi 2 is the angle, okay? This is the power factor. The power factor is the cosine of this angle here. The power factor is the cosine of this angle here. If we want to find phi 2, we need to calculate the inverse cosine. Then the inverse cosine, 0.8, is equal to 36.87 degrees. Okay? We have come up with the angle phi 2. Now we are going to use this, okay, to calculate the apparent power S2. Okay? The apparent power S2 is going to be equal to Q2 divided by the sine of this angle here, phi 2. Okay? 30 kVAR divided by sine 36.87 degrees. And if we calculate this, we find 50 kVA. 50 kVA. This is the second result. 50 kVA, 36.87 degrees. And the apparent power of the second load, this and the angle, okay, they make up the apparent power, and the angle make up the complex power. The complex power is not the apparent power. The apparent power is the magnitude of the complex power. So the complex power here is 2, complex power 2 is, as we calculated, 50 phase 36.87 degrees kVA. Okay. We have calculated the apparent power and the complex power of load 1. We have calculated the complex power of load 2. Now we need to calculate the complex power of load 3. Let's do it. Can you see how easy it is? Okay, now we are going to calculate the complex power of load 3. What did the problem give us? The problem gave us this. Okay, very simple. We need to do what we did for load 2, and we are going to do for load 3. We are going to use the power factor. Okay, so we have this for load 3, 10 kVA, and the power factor is 0.9 lagging. Okay, the power factor is the cosine of the angle. We have something of the sort. The complex power with a dot on top is equal to the apparent power, not three-phase, apparent power phase 3, okay? All right? This is the apparent power and this is the complex power. And how do we find this angle here? We simply calculate the inverse cosine. The inverse cosine of 0.9 is equal to this angle here. This is the power factor is the cosine of this angle here. The inverse cosine gives the angle. Okay, so the angle is 25.84 degrees. Then the complex power S3 is equal to the apparent power 10 in an angle 25.84 degrees kVA. Okay, this is the apparent power for load 2, and this is the complex power for load 2. Okay, now what we need to do is to sum them up. We are going to sum them all, and then we are going to find what the problem wants us to find. All right, guys. Very good. Very good. Okay, now the power of the transformer will be 10 minus J 2.5 kVA plus 40 plus J 30 kVA plus 9 plus J 4.36 kVA. Here it is in the Cartesian form. You can simply conduct some algebraic manipulations to transform the polar form from the polar form to the Cartesian form here. Okay, we found the polar form for load 2 and we found the polar form for load 3. Just conduct these algebraic manipulations and you are going to get at these results here that I discovered. Now, we are going to find that it is equal to 59 plus J31.86 kVA. And then what we need is to find ST equal to ST in a phase. Okay, we are interested in this here. Okay, we're not going to carry much about the angle because the result that we're looking for here does not it is not much related with the angle. What we need is merely the apparent power, not the entire complex power. All right, then we are going to simply conduct this. ST, the apparent power, is going to be equal to 59 squared plus 31.86 squared, and we're going to take the square root of it all and find 67 kVA. Okay, this is our final result. Okay, so the transformer that we need to use to supply these loads has to be a little bit larger than this. Okay, this is 67 kVA. Okay, the sum of the apparent powers of all these loads here, load 1, load 2, and load 3. And the one that we are going to choose is letter C. We're going to check letter C because B is lower and D is too high. Then the appropriate transformer for this kind of distribution system will be letter C. Okay? Very good, my friends. This is the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my contact WhatsApp number, guys. Goodbye.